Hello, everyone. Now you can hear me for sure. Welcome to this new appointment of the seminar cycle Highlights in Frontier Physics. I am delighted to have today here Professor Carlo Baccigalupi from SISSA. Professor Baccigalupi is a leading expert in physical cosmology, early universe, theory, analysis, and interpretation of cosmological and astrophysical observations concerning the CMB, large-scale structure, and gravitational waves. He took his master's degree in Pisa in 1995, and in 1999 he earned his PhD degree in Ferrara. Since then, he has traveled the world, working in some of the most prestigious institutions in the world, and in 2006 he became associate professor at SISSA, where he's now full professor and coordinator of the Astrophysics and Cosmology group. He has been awarded numerous grants and prizes, and he plays a key role in major international missions like LIGHTBIRD and the Simons Observatory. Now, I think this very brief introduction is enough to understand the quality of our speaker. So I leave the mic to Prof. Baccigalupi, who's going to talk about probe combination in cosmology, status, and perspective. Thank you.
Okay, thank you. Thank you for this invitation. It is an extreme privilege for me to be here for prospects in the collaboration between institutions and for affection that I have with my former student Giuseppe Puglisi, which is now professor in this prestigious institution. Okay, so this is an informal review of something that is basically is coming in cosmology as a major new perspective of things. And we won't be having details, we'll be having just a broad overview of the opportunities that the science of corresponding to cosmology is granting to people now, going beyond the use of a single probe, but actually having multiple examples of probe combination. Okay, we will carry out this discussion in these points, why it is important, the current impact of probe combination, prospects for the future, and final remarks. Before entering into this business, I added one bullet there, which is our network, because before highlighting again this structure, I want to summarize to you the history that brings a professor like Giuseppe and his group and activities here, and because it is very important. No? So we are all passionate in science and all those beautiful projects, etc. But we need to communicate and collaborate and to do networking. Okay, so several of efforts that we've been bringing forward, in particular in Italy, with several institutions and collaborators, started with this in 2016 with this network, which had a couple of nodes, and was supposed to engage science with different probes for that are studying the cosmic microwave background and all the activity. So we love science and we want to pursue this system. No, if you get together with your colleagues and you bring forward your ideas and you collaborate, you become stronger. No, and the strength makes the extension of the impact of this area of science, in particular, broader. No, and I am totally convinced that extending this impact of science, in particular in this perspective, is a very healthy thing to do for us as a community. No? And so it happens when you do the network, the networking. It happens. You know, you extend and you create new places in which these areas of information are represented by a person, which is Giuseppe here, that then propagates the knowledge to you guys, connect you guys with the other networks, etc. No, it's a very healthy system. No, it's a struggle. It's difficult to keep all this coordination. It's a struggle, but it is extremely beneficial. Okay, That's the context that I wanted to highlight in coming here. Now there is new contract for the Lightbird things for the Simons Observatory, here, and they are being discussed, and there will be notes, funding and meetings. We are planning meetings in this marvelous location that you guys have. Ok, va bene. Allora, why this is like for cosmology? Perché è vitale? Why is it? Okay. Okay, that's more or less the system of that we keep propagating this plot that I invented. It is extremely messy, and you have the red. It's just symbolic. Okay, you have the red shift with cosmological epochs and observables in this axis, and you have the era of
in questo mondo.
Excuse me.
I think it was a mistake.
I was okay. So we have the universe, and then the structure formation, and several situations in the middle. And here you can measure your expansion rate, the behavior of gravitational potentials in the many structures that are populating this part. So the main, there are several unknowns distributed in this system, but things we are talking about today are in the mysteries in the early universe and mysteries in the structure of formation. Because here you have mysteries like early universe, inflation, and etc. etc. Here you have the dark cosmological components. You have dark matter and dark energy, which we know their manifestations, but we have no idea what they are. So these things are, and this plot, they look very separated in terms of epoch. But no, everything is very much connected, and so in this plot you see an example of that, in which symbolically you see that you recognize the cosmic microwave background, and then you see a blurred image that it is what we actually detect. No, we will never see the CMB as it is in the early universe. No, we see a blurred version of that. Why? Because the photons are passing through forming cosmological structures. And so they do several things, including they are gravitationally deflected. And so, this situation is what, of course, this correlates, this brings in one signal the information from the early universe and the information from structural formation. And so, you immediately see that the information is combined. You need to understand exactly how all of that information is inserted here in order to recognize the difference. A curiosity is that with our cosmological model, the angular blurring scale is about 2 arc minutes. So if you zoom in the CMB and you try, this is exaggerated, you try to look at 2 arc minutes, you will see an effect of the blurring because the geodesics have been deflected. It's a small but very important effect. Okay, so
sorry, can I ask?
Yes, for sure,
No, but in the final picture of CMB, CMB map, it is already taken into account. It's already compensated or not?
No. They give you there are tools that correct your map and they bring you a lensed map, but the image that you see in textbooks, etc., has the lensing in. Okay, you don't see this pattern because here it is exaggerated.
Okay.
Qui è esagerato.
Okay.
But in the pictures, they bring all the CMB as it appears after integrating all the effects from the universe and from structural formation.
So you said that the lensing is there.
The lensing is there. Yeah, it's in those maps. Yes. It is in those maps. Yes. You may correct and bring it back to the original, but you have to have information on the lenses in order to decompose, And you don't have information on all the lenses. You have partial information in one direction of the sky only with a limited redshift interval. So those exercises are limited in the capability of reconstructing the faithful Okay, but we'll go back to this point, which is very, very important, because one area of literature in the CMB is called de-lensing, precisely because they want to subtract the lensing. We'll see why. Okay, so if you take the Fourier transform of this situation, you have your angle and power of the cosmic microwave background anisotropies. You see in effect that the several effects are superposed. The ones in blue, in red, are your universe. Here you have angles. So from 100 to here, you see from the degree or more. From 100 to there, you see the degree or less in terms of angular scales. And so on large scales, you have a more regular behavior of curves. This is total intensity anisotropy, the gradient mode, the curve mode, and their correlation. Because large scales correspond to unprocessed situation from here in the universe. The local phenomena didn't modify the distribution of structures, and so you see regular curves. Here you see a lot of bubbling, blum, 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 because those are the scales in which sound waves were propagating in the early universe, and when the CMB was free to move to us, it recorded that oscillations, those oscillations. The CMB, the cosmic microwave background, decoupled at a temperature of about 3000 Kelvin. And you know that the temperature of the atmosphere of a star, like the sun, is 5000. Okay, so very much comparable. If you look at the sun is bubbling. There are sound waves bubbling. Same thing for the universe. So if you look to scales which are below the sound horizon, you see lots of bubbling in the universe. Precisely, you see lots of bubbling in stars. Okay, so let's look at so how do we disentangle the different effects? So in this there are different effects. Basically, what we do is basically to describe mathematically the various injection of information at different epochs. For example, you can measure distances, which are incorporating the gravitational potentials, how they are related to matter structures, and you have one single layer. But if you start adding more layers of information, because you have more probes that are measuring structures at different epochs, you may say, oh, maybe I can break the degeneracy between various effects, and so forth and so on. So cosmology is now becoming an obsolete terminology. The updated version is tomographic cosmology. Okay, cosmologists are becoming doctors. They do tomographic analysis of the tissues with extreme detail. Okay, doctors do the same. They do tomographic analysis. Here you do the same. You launch satellites, you design telescopes, and you do several photographic layers at all epochs, and you do cosmology in each one of them, not in the entire system. Now, you look at a single tomographic layer with extreme detail, and you take into account cross correlations, etc., but that's what you do. So cosmology is now tomographic. Okay, and you discover marvelous things, in particular the phenomena like the one that we were commenting earlier on, the lensing, the reflection. It is interesting because it does several interesting things so here the region from where the photons of the CMB are coming, they are scattered in all directions and they cross structures, and some of them are directed to us. And so the distinction between the different modes of polarization are actually changing, and they get together. So the two measurable associated to the polarization of the background, the gradient mode and the curl compositions, are mixed together. And And so if you are interested in one of them, for example, the kernel component, because that's a pseudo tensor and contains the imprint of cosmological gravitational waves, you may say, there is a contamination from the others. I would like them to do. But contaminations are not coming without merit, without opportunities, because this process, the process of reorienting photons along their path, is actually happening when the universe starts accelerating under the pressure of the mysterious dark energy. So if one of your tomographic layer stays in that epoch, you are measuring the early stages of cosmic acceleration. So you may hope to check if it is a cosmological constant or not, and helping the other probes. Okay, so this analysis provides opportunities, connects everything with everything, and provides new insights into mysterious phenomena. Okay. You find also interesting works in which you precisely, by moving the dark energy equation of state and the energy density moves accordingly, that moves the Hubble expansion rate, and so the region in which the lensing is important is here. We can take a second to describe this curve here. This is the kernel component of the cosmic microwave background polarization. So if you talk to Giuseppe, he will tell you that the entire globe is after this signal. No, it's very low. You see this. You are familiar with the acoustic peaks of the CMB, and you have seen the E modes, the modes. All this bubbling here, similar to the bubbling of a star, is actually originated by scalars. So by density perturbations. You see that the spectrum of the kernel component is very different. You see 3 peaks, no bubbling. No, so you may want.
Which component is that?
The kernel component. It's a B. So the polarization field, classic polarization, nothing complicated. Classic linear polarization. You can decompose your polarization tensor in one part, which is a gradient, and the other, the leftover, which is a kernel component. The kernel component, because of its parity, is excited by cosmological gravitational waves. Now we'll see why in a second. We check
have some analogy with the star in this sense.
No, not with the star, because the star, and that's what I was saying. The star, the bubbling, is originated by density perturbations. Gravitational waves are not density perturbations, so they do something else. Okay, and precisely in the cosmic microwave background, they do this. So if you perturb with gravitational waves the sun, and you look at it in its response, you would see an equivalent of another component into its properties. Okay, no. There are no probably big, so, okay. Okay, this is the part. So more or less the community has knowledge of this part here, so it could be better, okay, but this part here is very poorly known, and it is done in this manner because of the following, okay. Forget this and forget this for a second.
So,
see,
what happened at the spikes? Locations. They are singularities.
Because good point. These spikes are the point in which this is a power spectrum. So the points in which it become negative. So you have positive correlation, anti-correlation. Exactly. So in this plot they become negative. So these are the zeros. Zeros. Okay, forget this peak for a second. So we see something here which is a peak. Okay, around L equal 100. So this, and let me check if I put it somewhere. No. Okay, I should add 2 slides for that. Okay, and okay, so it is very intuitive to understand. Cosmological gravitational waves are basically distorting space-time around in the region in which the CMB photons are scattered to us. And if there are gravitational waves around, one component of the CMB polarization is bringing that signal to us. Now you may say, what is the distribution in wavelengths of cosmological gravitational waves? Usually they are distributed on all wavelengths because that is early universe phenomenon. So which wavelengths are brought to us by the CMB? Not all of them, because on large scales, there is no time for photons to hit an electron from very far away and come to us. So you have a decrease here. On small scales, gravitational waves are not supported by density or gravity. They are massless and they have no pressure effects, and so they decay very quickly. Okay, so the various numbers, cosmological abundances, epochs, etc., conspire to set the degree, the recording of cosmological gravitational waves in a single angle, which is the degree in the sky. So the CMB takes a snapshot of cosmological gravitational waves on the degree scale and brings those to us. You may say, okay, fine, and we understand this central peak here. And then you say, what are these other two? Okay, first, this second peak is, which is generated here, it is reionization. So it happens that photons coming to us are hitting free electrons again from cosmic structures. They rescatter and they amplify a bit the signal. Okay, this is the reionization peak. This other part here is actually the lensing. If you look, so the fact that photons are passing in the middle of these structures and they leak from E to B. And if you look closely, you even see the scars, because you see scars of oscillations, which are precisely the oscillations in the E modes brought down by the leak. Okay. And so is the situation. So we have all these effects combined together in one single observer. No, okay, fine, but no, could be worse, because the lensing is, because those are different processes, so they usually contribute most at different scales. Okay, so the lensing you see is on the arc-minute. Gravitational waves are on the degree and tenths of degree. Okay, and so could be worse. You understand, no, that despite of all the discussions, etc., that we are having to Giuseppe and our collaborators in front of agencies, funding agencies, we as a human species, we cannot live with these observables, which is the oldest picture of the universe we can get, by observing 1, 2, 3, and not observing these, no, because we don't know, no. So that's a fundamental knowledge of this process, the lensing, possible gravitational waves, reionization. Okay. And so do we have the technology to do so? Yes, we have the technology. So no, we cannot observe the CMB, 4 quinti of the CMB. No, and no. That's science. We observe it all, completely all of that, no? And so we are gently pushing this part, and we said in the beginning a little historical anecdote is that in the beginning we were saying, just give us one monster satellite, a post-Planck and a normal satellite, no, not a normal, super powerful satellite, which goes into space and measures this, whatever it is. No? And they said, are you sure that the gravitational waves exist? They said, we are confident, but not sure. I said, no, then if you don't have if you are not completely 100% sure that the signal is there, then we don't pay for another satellite. No, do telescopes. No, and we're doing telescopes. And now we are proposing another satellite. So we just looks at this. No? So the sum of the money that they have to spend for all these telescope 1, telescope 2, is much more than a single satellite. No? So they would have saved money if they believed to us. But they're fine. So we are going there with a system of detectors in Europe, in the US, and in other locations with all the various fragmentation stuff. Okay. Anyway, that is the anecdote, and we are there. So
can I ask a question?
See?
I understand that the peak for the reorganization is in this exactly in this angle, and the one for gravitational lensing. Yes, here. Why precisely on this at this angle?
Why the lensing?
Yeah. Like,
because
if I understand well, this is like
this is because you have it in front of you. The scattering is close to you, so everything that you see is on larger angular scales. And these things instead is determined by the distribution of the source, which is the CMB anisotropy, and where the lenses are. And they are far away. Lenses are mostly very far away for CMB lensing, and so everything is far away, so you have it on the arc. Okay, promise of CMB lensing that we already said. The lenses for the CMB are very far away at infinity, so the lensing is basically probing if the cosmological constant is a cosmological constant or some kind of dynamical component very early in stages of cosmic acceleration. No? And so, this blurring of the CMB helps you a lot in the early stages of cosmic acceleration, and adds as an extra tomographic layer with respect to all the others. Here you have structures, quasars, galaxy, etc., in which you do tomographic analysis. CMB lensing is an extra tomographic layer from which you can get interesting hints on the early dynamics of the dark energy. Okay, together with this, in order to do this, so we want to do tomographic cosmology with all this. We are putting many probes, one after the other, and yeah, okay, fine. But then we have to produce to be able to simulate all of these. Otherwise, how we need to compare it, and we extra accuracy. So we need to start from the CMB anisotopes, evolution. The zoom, then populate these little tiny dots with dark matter, assume models of the dark energy, be able to simulate the formation of structures, etc. You have to simulate all these things. And so simulations is also an increasing attitude of cosmology for obvious reasons. So the tomographic layers are with unprecedented details, so you have to simulate things with unprecedented detail. So here you have gas physics, high temperature, thousands of kelvins. Here you have the structures. So it's good. The systems here is completely different. So you have exquisite care into the various aspects, and better to be accurate, because if you are not accurate, given the level of accuracy, you can misinterpret things and getting wrong measurements of wrong things. Okay, so, and there is an engineering of parameterization in dark energy, and you have the background is various in simulations. Various recipes, equation of state as a function of redshift, direct vision from models, and cosmological perturbations. And so you may have seen plots of this kind, in which the dark energy is the equation of state, the ratio between pressure and energy density is written in this very simple way. And by combining the different tomographic layers, they try to measure these parameters and these parameters. So the equation of state, or let's say the equation of state today of the dark energy, and the first derivative with respect to the scale, with respect to time, the scale factor. So, and there is one beautiful probe in these months, which is DAISY, that reported tension between their data and the cosmological constant. Okay, and that needs to be scrutinized, analyzed, understood, etc., but that would be a major breakthrough, no, if the dark energy is not a cosmological constant. We need, but it is relevant to quote those things here because if you read those papers, they are all probe combination. There is no single analysis that is done on, the validation is done on your data by DAISY, for example, but all the cosmological constraints are done by combining everything. So you see, probe combination is in everything. Okay, so you do this parameter, or you are an agnostic, and you do the beams in redshift, and you want to measure this each values of the equation of state in the different beams to see which kind of curves those constraints are allowing. And the power of SIM probes now is represented by the Euclid satellite that we are quoting in a moment, in which the power, the strength of the probe, of the Euclid satellite, which is flying now, it is beyond the moon, is such that that monster will be basically measuring the dark energy equation of state between redshift 0 and redshift 2 10 times, 10 photographic layers, with % precision each. Okay, so if the cosmological constant fits all of the data, fine. No, but it is extreme accuracy, an extreme attempt to find a physics into the cosmological constant as it appears now. Okay, tomographic analysis. So Euclid, is not a single probe which does a global cosmology. It also does global cosmology, but the main task is to do cosmology in 10 slices. Okay, the final parameterization is also by former student Marco Raveri, which years ago took all the data and designed the curves with uncertainty which fits all of those, just to give an example of how complicated getting the various constraints of, for example, experiments can be. And you have funny shapes of the equation of state of the dark energy. Okay, no equations. All these things require calculations which are largely linear, and they may be casted in several manners with a well-defined mathematics that is actually. So you can see.
Regarding the plot that you show in Valladolid, but this doesn't say that. That means to me it shows somehow that this parameterization, this linear parameterization, does not really work, or.
As you see, this what you see here is the inverted problem. So Marco, at the time, it was 2017, took the various data that were available at the time and determined, which were constraining the equation of state, determined which best curve would fit all of them. Finding, he reported tension between those data and the cosmological constant with accuracy, with level of discrepancy which was increasing by going in high redshift because you don't have any.
And the color area are constrained.
The preferred value of the dark energy in that redshift interval. Okay. If you do this plot now, it will be completely different because probes have been changing. This is an example of the third example of you can do here. You can do toy model for parameterization. You can do principal component analysis, or you can also take the data and try to free completely the curve of the equation of state and try to see which behavior satisfies all the constraints. Okay, so these three methods have been explored in the literature. They will be used for the data various props. Okay, so you have you can start from a theory that I've all the relevant equations, or you can say, there will be a modification in gravity, so the gravitational potentials will be different from each other by a function which will model and constrain. The equation relating gravitational potentials and matter would be changed by phenomenological functions and so on and so forth, and you constrain those phenomenological functions. Okay, okay. Are we there with precision? For example, in the CMB lensing, in order to be aggressive and check if the beginning of cosmic acceleration was really thanks to a cosmological constant, or there was some dynamics at those early stages. So you need precision, and for this particular observable, we are not yet at the level of precision, which is this is a recent combination of details. Now the situation is a bit better, but not that much, in which you see that the predicted curve from lambda cosmological, from the standard cosmological model is the best fit, but with precision that needs to be improved in order to be extremely aggressive with the cosmological constraint. Although we are in a good direction, the lensing, the signal is there. We put several measurements of these. These are 20 beams. You can compare those 20 beams with the 2,500 multiples measured by Planck, for example. So we're not yet there to that level of precision, but no, it's promising. Okay. Now, is probe combination having an impact at this moment in cosmology? The answer is yes. The impact is already microscopic. Here, I show you the two extremes of the story, and the very early stages of measurement of in probe combination, and what is happening nowadays. In this slide, you see very early stages by Federico that was also studying in SISSA. I think a paper was there. And here you see two fields, and these fields here are the cosmic micro background anisotropies in total intensity, as seen by Planck. And here you see the lenses as traced by galaxies by another satellite, the Herschel satellite. So, in the observation of and this is 2015, in the observations of the cosmic microwave background, there must be the blurring that we were talking about earlier on. Blurring due to lenses. And so by cross-correlating these fields, we should be able to measure the expected level of cross-correlation. And you see that also in that case, it is spectacular to see that the signal is there, and it is with very rough precision, of course, but it is there. Now, the two fields, these are galaxies and these are cosmic microwave, have something in common. And the reason is that the photons passed through these structures before coming to us and recorded their presence through gravitational deflection. And Federico, it's a struggle. No? Nowadays, those things are much more powerful. In the beginning, when you have a new signal, you struggle with the signal. So Federico was calculating the covariance with various ingenious mechanisms, comparing the precision in different methods, and so it was quite painful and with unknown manifestations. For example, something that nowadays is not happening anymore, but the amplitude of the lensing was coming out to 1.5 sigma intention with the predicted level, for example. But still, we were able to see the evolution, early insight in the evolution of the bias, which is the ratio between luminous matter and dark matter, as a function of redshift, as it should happen in the cosmological with a hierarchical structure formation. So, and the signal is there. Now, we jump to the latest example that I already anticipated, which is with the daisy. The daisy, you do this, and look at that. From combination, no, there is no daisy only, no. And you may do the classic plot by considering the equation of the dark energy as a single parameter, constant, okay, and you recover the familiar value, but the data sets are becoming bigger and bigger and bigger by daisy to be combined with the others, and so if you open the parameter space, you find a little bit of a tension, no, and the cosmological constant, which is here, is disfavored by this analysis to a level which is about 2.5 signals. And so, is that significant, statistically significant? Well, no, not yet. We need to be careful in several aspects. And in particular, there is one caveat in all of these. Now, you know, and we have to be careful when we do, to forget those biases when we do refine models. And the caveat is the following: you know that the cosmological constant is a constant, not constant in time, in space. But if it is dynamical, you have to allow for spatial perturbations of that, like matter, like photons, like everything, no? Because it is you cannot, in general relativity, you cannot say an object is dynamical only in one coordinate, no? It is forbidden. If it has dynamics, it has to have dynamics in all of the four components, also in spatial perturbation. You may say, they will be small, linear like the others, but it has to be. So all these constraints are computed ignoring that part, okay? So now, fine. We approached them and told them this part. They responded in a fair manner. They said, look, we are just doing a sanity check here. So they said, if the contours were here on the cosmological constant, we say fine. It is a cosmological constant with an error. We don't insist in modeling. But if, as it is happening, the cosmological constant is in tension with the preference of the data, then we give this, in this simplified modeling in which we don't have fluctuations, we give these results to people, and people will start to recalculate spectra to forecast better, okay, which is a very fair answer. And so that is what they are now reinspecting everything. In case this should be confirmed or even getting stronger and stronger, no, you will see papers appearing reconsidering spatial perturbations for the dark energy as well, if the things become serious. Okay, for now, we're still with this mild tension.
Which kind of observational effect could have spatial perturbation?
But years ago, when the dark energy was modeled as a scalar field, there were very clear say effects. Essentially, if it is a field, it is very light. The mass is extremely comparable to the critical density today is very low, so it cannot cluster on galactic scales or star scales or so it was calculated that for values of the equation of state in this area, no, it should provide power on scales corresponding to hundreds of megaparsecs or more. So if you do the spectrum of the density, you should see at some point a little step, because the field clustering is active on those scales. That is for sure one of the basic signature of that. So in case this situation persists, you will see that the authors already start to consider that to refine those calculations, and maybe looking into the data for such an effect. No, we are very far from that. Okay, they are inspecting the data, checking everything, reporting in conferences, fine. But this is the situation. And we have to be open-minded, no? And so the cosmological constant is funny, but we'll see. It's certainly something. Okay, now this was one of the some focus on some of the effects which clearly correlate something very early, which is the cosmic microwave background, with something very late, which is the dark cosmological components. What about those probes which are observing these aspects? And no, the agenda is extremely full of these things, and rightly so, and that's why we need networking. No, this has to be a global effect, a global collaboration, with many nodes in each single country. So we have a Euclid satellite finders, previous surveys, so a battery of operating cosmological probes, frequencies of band, observations of bands to look at contaminants. And the Euclid satellite, the Vera Ruby, this is the Daisy and Des, the Roman telescope is about to be launched. And plus, there is an entire new roadmap corresponding to gravitational waves, which are also traces of the dark matter, of the distribution of matter, because they are originated in galaxies and so on and so forth. And so, no, and it is a huge insight of information. We need people, machines, even digital intelligences, and networking to carry out all of these. Otherwise, that's only up to 2025. Accidents happen because of the fragmentation. The fragmentation is something that I will give you as a final twist of our discussion. So this S4 is transparent because it has been essentially cancelled. All this knowledge is to be projected in the globe. The globe is very much fragmented. And so you have single point failures, because if one administration goes nuts, then it may cause perturbations to your system. So the CMB-S4 is the system of telescopes that was supposed to be deployed, most by Americans, poor guys, in the 30s. And the new administration canceled that completely, promising more money for this. And I knew that now they are already after 6 months, they are already saying, maybe, see, more money for you, maybe, yes. No, so they fregori. Anyway, and so the important point to notice is that administrations have no competence in science. Zero competence, zero. So the fact that one of them cancels one of our programs doesn't take the necessity of this program out of the table. So the scientific question is still there. The administration, because of its business, may say, no, we are not going to do that, but the science case stays on the table. Okay, so they may have problems with resources. Okay, the cost even of this program is immensely inferior with respect to any other craziness which is around in these years. Okay, orders of magnitude that Nevertheless, they may say, no, we're not going to do that. Fine, but the scientific question of, in this case, which telescopes do we deploy on the ground in the 30s in order to see if to improve on the observation of this is still on the table. No? That's our business. We know the scientific question is well posed and it is on the table. And no administration will take it out. Okay, give you just examples of the first part, this part and the second part, and then we're going to the conclusion. For the first part, things which are operating now, I couldn't not avoid quoting the marvel of the UCLID satellite, European Space Agency. And here we can say in something that you guys have to notice, no? So the European Union has many problems, fragmentation. Let's say it is slow, etc., etc. But some of things are working in a virtuous manner. For example, the sequence of satellites, they are only in cosmology, is excellent. So they founded the Planck satellite, which is in the textbooks around the world as a basic knowledge of the cosmic microwave background, as a heritage and legacy of that fundamental observable. And when that was finishing, they said no to a future CMB satellites, but they approved this other monster here, this Euclid satellite. So you see, in those offices of the technocrats and the people dealing with those things, there is some illumination there, and they get the proposals and they try with their own capabilities to convince all the various offices and then organizations to pay for these monsters here. And 10 years later, you find this revolution ongoing. The level of detail is not represented by these pictures. You see a cluster here. You see galaxies until things. You can see, this is the total vision in one portion of the sky. So you can divide these things in layers and do tomography on this study and compare with your simulations to see what the dark energy is doing. Okay, now that's a monster. You find the data here. Those are objects. It is so 4 meters and something, 2 tons, and other things. So about 1,000 people working on that. It is producing the Q1 papers, and it is entering the data releases, targeting data release 1, in which the fields are being inspected. This is one part with this part of the sky, with this level of detail, which you see distant objects, which have unprecedented resolution. And various years of observations within these regions, some of them earlier, some other later. These things we observe for 6 years and more, and providing you with the necessary information from data. 3 data releases so far. The last one is the 6th year after the launch. And can I tell a little the anecdote of the launcher? Maybe you guys know.
Yeah, I think.
Allora, sì, it has been launched, luckily, but there was a crisis in 2022 because of the war, precisely because of those administration going funny. So it was supposed to fly on the Soyuz, and from the start of the war, the Russians disappeared completely. They became completely hostile from one day to the other, and there was no way to bring forward this project. So there was a crisis because the satellite the satellite was ready for launch, no? And so, and what we launched, and for the European launcher was very much behind schedule. And so they were basically desperate, no? Because you can imagine what it means to keep a satellite like Euclid in the garage until further notice. No, okay. And so the PI announced a global survey of all possible launchers in the Oslo meeting in 2022, and that will be concluded by the end of 2022 to check all possible launchers that can launch our beloved satellite. We are in the class, and then remember that nobody raised the hand, but in the audience, while the PI was announcing this, there was somebody already whispering, saying, "Did they ask SpaceX?" Okay, it was already almost. And then, a few months passed, and then the PI called us in the final part of the summer, saying, "This is a total secret, but we are going to launch with Falcon 9 SpaceX." Okay, and we said, "Okay, fine, good." Somebody was complaining because they said, "No, we give power to them, etc., etc." But overall, they said we cannot keep Euclid in a garage. No. And then the PI said, "But this is completely secret. Nobody should know because we have to announce it later in the year, etc., etc." And then I said, "Sure, I'm not saying it to anybody." Then we hung up, and I woke out of my office, and there was my postdoc, Sandeep Haridasu, that came to me and said, "Is it true that we launched with SpaceX?" So they knew that already. Okay, fine. The SpaceX was just asking to change the lower part of the satellite for the link to the spacecraft, and they launched 8 months later with perfect performance. Okay, and this is the promise, the promise of precision in the matter power spectrum in the weak lensing. I'm not, and these are forecasts that you find in papers, and exquisite pipelines are going to be implemented in order to construct the simulations. Okay, we are going to finish now with the examples of what will going to happen in the 30s, and we are focusing on this person here, and the Simons observatory. So this family of 2 CMB probes of the 30s. Okay, forecast, because the Simons Observatory is at this moment observing with forecasted precision on the B-modes that you've seen here. Okay, much better than now, eh? Okay, and these are preliminary. It is operating, taking data. These are preliminary maps, true data, or just a couple of weeks of data. Small aperture telescope, middle frequency, compared with Planck. You see that the structure corresponds. There is more angular resolution in the Simons Observatory. Okay, this is coming, few months, first papers will be out. And preliminary, in the Stokes parameters. Oh, and now we're going to finish with this object here, which is the Light-Bear satellite, for which Giuseppe and I contributed as much as we could. And this is the fourth, advanced proposal, so about to go in phase A of a fourth CMB satellite for catching this part of the spectrum in the B modes in order to focus on gravitational waves. And you may say here, but okay, you have ground-based and a satellite. And why do you need the 2 of them? The reason is that we need to observe the entire spectrum of B modes from here, from the arc-minute scale, the quadrupole, because the signal is populating all of those angles. And because They didn't want to pay for a single monster satellite, so that does everything. Okay, we are going with a ground-based strategy, looking at degree and sub-degree angular scales, and with a large-scale strategy from the satellite, which looks at large angular scales. That's what we do with the probes that they gave us. The other reason for which we are going with separate probes is scientific. The B-modes are very low, you see, and there are many contaminants, instrumental systematics, even our own galaxy. We are observing from the galaxy, no? It is emitting in polarization, confusing all the signals. So lots of contaminants versus an extraordinary claim that we could do. Because if we discover gravitational waves from the early universe, from the inflation, that would be a major discovery at all times. So if you want to do that extraordinary claim, if you see the signal and you want to have validation, you want to convince it. Nobody will believe us if only the Sinus Observatory sees something, not the satellite, or vice versa. Plus, space, looking from space, is the best location first, but it is the unique location which is able to measure the signal from cosmological gravitational waves in the two peaks. The original part at 1 degree that we said at the beginning, the original snapshot, and the reamplification from a realization. So those inter-validation procedures will help us validate if the signal is there to be convincing with these things. Okay, and the CMBS4 has been cancelled, etc., etc. And there are in these probes early examples of probe combinations in which the various probes are being combined in order to do what was asked at the beginning, and I will just spend 10 seconds on that. But with the information on the lenses, you can partially predict the deflection, and you can subtract some of the power from the lensing to gain insight into the primordial signal. That's a huge part of literature with simulations and activities there, which is truly probe combination, and it is already active. You don't see many of these results in data yet, because they are preparing the tools and the okay, perfetto. Okay, so early on, years ago, collaborations were getting together just for specific science targets. No, now the common objectives are so numerous that these things are becoming normal. So there are memorandum of understandings, those things that collaboration A does with collaboration B, but they do not specify anymore the single goal, because they say they prepare just those agreements as umbrella for all the various aspects, that scientific aspects which are being studied. Okay, so this is becoming very much common, and basically everything is connecting with everything. For example, Euclid is connecting with the Sinus Observatory, which is connecting with Lightbird. Euclid is connecting with the Vera Rubin. Sinus Observatory is already connected with the Vera Rubin, etc., etc. They are, of course, doing agreements. So, and that's very important element for you, because if you enter in the here, on here, or here, okay, it is becoming less important from where you access these realities, because for the main cosmological measurements, they are actually, they provide you a network in which you can work with colleagues from other probes for your part. Okay, so there are huge opportunities now. Probe combination is mainstream in modern cosmology. The question is are we ready for this part? And for this question, we have two answers. The first is scientific. Scientifically, yeah, we are ready for this. Now we have curiosity. We can implement large-scale simulations. We are ready for surprises, etc., etc. From the organizations, so we don't know. This area here represents the distribution of countries with space agencies in the world at this moment, and you see that the system is very much fragmented still. No, so you can imagine those marvelous ideas: dark energy, dark matter, early universe, gravitational waves. You have to and you know which probes would be good to measure those things. You project this situation in this your goals into these fragmented systems, and you get you are into a chaos, because the agency here doesn't talk with you there, and the protocols are different, the phases are different. So who pays? I don't want to pay. Yes, you pay. I paid last time and I don't want to pay anymore. Etc. Then these guys are committing suicide, completely totally dead, etc., etc. Luckily, Ukraine is entering the European Space Agency, and so the fragmentation provides. Nevertheless, insisting on making everybody talking to everybody is a good service that we, as a scientific community, we can give to them, no? Because they learn that there are projects which are so important, so beautiful for general knowledge, that we are knocking to all those doors to ask them to coordinate with each other. It's not a problem of resources. Resources are there. It's a problem of coordination. Okay? And so we will insist in this. Thank you.